I guess it's part 2 of chapter 3 or unit 3 lesson 5, and that's differentials, which is really another way to look at linearization. So you need to be able to find differentials, and if you can do derivatives, that's pretty darn easy. Hopefully you can, by the end of this, have a little bit better understanding of what they mean. And then a major use of differentials is to estimate change. So you should be able to do that if you can find differentials. This is one of those things that I think you're going to be able to do first, and that may take a few times to understand what you're doing. So we have some graph called f. My goal here is to get you to know what a differential is based on things you do know. So delta x and delta y, those are pre-calculus ideas. That's simply a subtraction or a difference in those things. Like in delta x is, x2 minus x1, delta y is y2 minus y1. So we can think of those as side lengths of a right triangle. You should probably be thinking average rate of change here, right? Delta x is just that horizontal side length, because that would be x2 minus x1, and delta y would be that vertical side length. So a differential is based on the derivative slope at a point, and dx and delta x are both about change in x, dy and delta y are both about change in y. The difference is we're going to take that straight line approximation, that tangent line, and we're going to multiply. Delta x and dx are going to be the same thing. The difference is that dy, using the straight line approximation to find the estimated change in y, that's going to give us an error. And you can see in this diagram, this vertical distance is the error. Why would we do something that gives us an error? Because it's pretty darn quick. And I put this slide in for the kids in my class, as we're going through. Success today is just going to be, hey, can you find a differential? And you will be able to. Can you use the differential? Sure. Do you understand what it means? We're going to get there. We'll just keep asking. We'll keep repeating. You got this. Relax. Breathe. So the first thing to do is find the differential dy for y is equal to the square root of x. And you might be thinking, well, I don't know how to do that, but you kind of already do, because if you take the derivative of y equals the square root of x, you get dy over dx is 1 over 2 times the square root of x. And when we say find the differential dy, oh no. When we say find the differential dy, we really do mean that dy. Remember, dy dx is change in y over change in x. And so that's the thing we want. So how could we get that dy by itself? We multiply both sides by dx. So the differential dy is 1 over 2 root x times dx. I don't think that's going to be a hard thing for you to find. Okay? Now what does that thing mean? Dy is what we're going to use for our estimated change in y. 1 over 2 root x, well, that's the derivative part. That's how we're going to find the slope of the tangent line. And we are going to multiply by dx. And dx is a change in x. So you have a slope times a change in x, and of course you get a change in y. We just know that because we're using a straight line approximation, that dy and delta y are going to be different. Dy is going to give us, well, a little too much or a little too little change depending on concavity. Okay, so let's do it again. We're going to find the differential dy for y equals the square root of x, which we already did. Dy is 1 over 2 root x. Again, we take the derivative, multiply both sides by dx. And then when x equals 64 and dx equals 1. Now, you might not know what those pieces mean, but you could still guess about what to do. Where do you put the 64? Well, you put it in for x. And where do you put the dx? Or what do you do with the 1? You put it in for dx. So we get 1/16. What the heck does that mean? Well, don't forget, dy is an approximate change in y. So let's think about what we wrote down. We had x is 64, delta x and dx are kind of the same thing, so we'll just call them both 1. So really, we're talking about something happening at 65. In fact, we're talking about the square root of 65, because that's 1 more than 64 inside the square root. And what did we get? Well, we got dy is 1/16. We got the change in y is approximately 1/16 going from x equals 64 to x equals 65. 1/16 what's the best way to say this? The square root of 64 is 8. And the square root of 64 plus 1 is 1/16 more than 8. That's what we found, the approximate change in y. And if you are in my class, we did this exact same problem when we did linearization, because this is the exact same process. We just did it without explicitly writing the equation of the tangent line. Okay, so if you want a type diversion, here you go. 1/16 is the approximate change in y value on square root of x from where 64 is, and, well, we said it down below earlier. Well, I don't know why that's there. I'm going to pause for a second and figure out what's going on. I do not know what that slide was. I guess I was cutting and pasting and put a wrong slide in. Okay, so hopefully you can see that linearization and tangent lines are basically the same thing. We're just not writing out the tangent line, because in either case we're using a straight line to approximate a point nearby. All right, so we're going to find the differential dy if y equals x squared. How do we do that? Well, we're going to find dy dx first. Maybe we didn't. Okay, maybe we'll write that first. Well, dy dx, that's 2x, that's pretty easy. And we want dy by itself. So we multiply both sides by dx and just write 2x dx. So hopefully, eventually, if that's easy for you, you could just jump to dy is 2x dx. That's all there is to it. Now, what did we find? Oh, I forgot there's a little bit more. We're going to evaluate dy for x equals 2 and dx is 0.2, which really means we're finding something about 2 plus 0.02 squared. And we're finding out how much change there is, how much we would add to, well, I have a picture coming up, so we'll get there. But hopefully you realize if x is 2 and dx is 0.2, we're talking about what's going on at 2.2 in the function x squared. Okay, so of course we put 2 in for x and 0.2 in for dx, and we get 0.8. Now, what the heck have we found? Here's a diagram. So the known point on x squared is 2, 4. 0.2 here, that's our change in x. That's also dx. They're interchangeable. Okay. And what we found is 0.8. We found that in order to estimate the y value at 2.2, we would have to add 0.8 to the known y value 4. Okay. And again, why is this an approximation? Well, I need to get rid of some stuff. So this 0.8, that's dy. That's the approximate change in y. The real change in y is this vertical distance between 2 and 2 squared and 2.2 squared. All right. So here's a diagram down below. We're going to find the differential dy if y is sine of 3x. And sine of 3x has a period of 2 pi thirds. So I've graphed quite a bit of sine of 3x. And of course, the derivative of sine of 3x is 3 cosine of 3x. We just multiply both sides by dx. You'll get used to that. So to evaluate dy when x equals pi and dx is negative 0.2, really what that means is we're estimating something about sine of pi minus 0.2. We're doing something a little bit to the left of pi. Now we're not getting, well actually in this case we are getting the y value because sine of pi happens to be 0. But we're not getting the y value, we're getting a change in the y value from sine of pi to sine of pi minus 0.2. Okay, anyways, so we put in pi, 3 cosine of 3 pi times negative 0.02. And we evaluate, cosine of 3 pi is negative 1. Yeah. Is that right? That's not right. Sine of 3 pi is negative 1. Cosine of 3 pi. Is that 0? Oh, my brain isn't working at 5 in the morning. Let's see. Cosine. Oh. I was thinking 3 pi halves. Oh, yeah. Cosine of 3 pi is definitely negative 1. Okay. I feel better now. Okay. So we get 0.6. And what that means is that sine of pi minus 0.02 compared to sine of pi, right? Our new one is 0.06 more, right? That's the approximate change in y. All right, let's do one application, then we'll call it a day. We're going to write a differential formula that estimates change in volume of a sphere when the radius changes from 10 inches to 11 inches. So this almost feels like related rates. The volume of a sphere is 4/3 pi r cubed. If we're estimating change in volume, we want dV. And when the radius changes from 10 to 11 inches, that means the radius starts off as 10, and the change in radius is equal to +1, which also means dr is going to be +1. Okay, so we take the derivative of both sides, and previously we had dV dr. Multiply both sides by dr. But again, you'll just get used to not having that, is 4 pi r squared dr. And then, well, we've already figured out that we were going to use the radius of 10, and it's a delta r of +1, which means dr is also +1. And so we get dV is 400 pi. And, I guess why would we do that? Well, it's a technique. It's used for estimating purposes. If we really wanted to know what the actual change in volume is, that would be 4/3 times pi times 11 cubed minus 4/3 pi times 10 cubed. Right, that's what we're estimating, the difference between the volume of these two spheres. And you can see what we did is super straightforward, and it gives us a pretty good estimate. It's not terribly close, but it's not that bad. I'm not going to multiply everything out. 1,331 for 11 cubed, but you can do that if you want. All right, hope that helped.